Hi folks, welcome to the FZX2 How-To series. Video number 3, we're going to talk about making measurements with the FZX2 software. So first we're going to go over the last of the two main objects, and that's the wire factory and the sensor plane, or actually sensor plane 2. The reason why these work out good is because these are actually part of taking measurements. So for those people that are joining us in the middle, what is FZX2? FZX2 is a simulation tool that uses new electromagnetism V5 field models to compute forces and or voltages between wires, magnets, and charges. These are the experiments that validated. You can see little magnets here. This kind of matches this guy over here. If you want to see a brief synopsis of the experiments, watch the first video in the series, or you can watch the entire new electromagnetism V5 series. Okay, the first thing we're going to talk about is improvements. Okay, last time with the rectangular magnet we had do not use for rotating experiments, need to add segmentation, and I was going to put that in physics at 2.02. If I say physics 2.2, I mean 2.02. Okay, and I got to thinking, I'm like, gee, we're going to be using this for a long time, and it's probably not a good idea to leave any landmines, because if we decide to use rectangular magnets in the future, I'm in a rotating reference frame, I might forget about this. So I decided that we're going to finish adding the segmentation. I added a whole bunch of other things, including the ability to see the segmentation. Okay, so if you turn view segmentation on, it'll give you alternating filaments. Will have alternating gold and silver color. This will not affect the material properties. This is just for display only. Okay, but we're going to have a whole section of this video. We're going to show the importance of segmentation and compare that to what we would call fragmentation. We'll talk about all of that later, once you learn more about measurements. Okay, part of the segmentation controls is show segmentation, which turns this on, changes it from that yucky purple color into alternating segments. Over here you can see if segmentation is off, which if you set segmentation length to 0, then you get one segment, one filament along each side. Once you set the segmentation length to a non-zero value, in this case it's 1 centimeter, and you can see that we got 1 centimeter, almost exactly 1 centimeter. What this thing will do, it will change slightly the size you specify so that an even number of segments line up on a side. The reason for that is it's not good to have uneven segments here, because if you're trying to debug it and you get a whole bunch of whole segments and an odd one at the end, that can make it difficult for debugging. So we want an even number of segments, and we will internally, the software adjusts the segmentation. It'll actually make it smaller if it can to fit an even number of segments of the same length, or not even number, but whole segments on the length, so that the segments along any given length are of uniform size. This is the new object repository for physics version 2.02. And let's get down to the filament is the first thing. I think we talked about it briefly. You can use the filaments separately if you like, but I'd recommend that instead of using filaments, use the wire, the F2 wire, because the F2 wire is a collection of filaments. And this has lots of controls for laying down very complex wire structures, and it takes care of segmentation and inserting impulses. These are the wire factory variables. What these mean is these variables all have to be set before you start laying down, inserting filaments into this. Okay, because every filament you add is going to acquire these properties here. So you set these first, and then you start laying in your filaments. What this allows you to do, in the middle of your wire, you can change the properties, so all the subsequent filaments you lay down may have a different material, a different wire diameter, whatever. It gives you the ability to change as you go, but this will automatically set these as you lay filaments in. After this, we have the factory controls. Remember, these are the factory variables. These are the factory controls. These are the filament primitives. Pretty much you should not be using these. These are used by the higher level controls, which you should be using. Okay, I'm not going to explain these to you because I don't really want you using them. Okay, and the way you can tell the filament primitives is they all take filament as their input. Okay, these do not do segmentation, but these are used by the higher level controls to do segmentation. Okay, the first part of the higher level controls are called the Z-plane controls. You can tell them because they all have a Z at the end. These allow you to create really quick flat armatures around the Z-axis in the Z-plane. So, and we're going to give an example of this, so don't worry, I'm just going to show this real quickly. This is from the Paradox 2 D-wire experiment. This is right from it. This is cut and paste right from there. In here, though, we have a separate wire for every part of the loop. And the reason why we did that was to see how each of the loop is affected by the magnetic field separately. In the example we're going to do, we're just going to lay down one continuous loop. The other factory controls are the freeform controls. There's going to be an example of the freeform controls later in this video and a much bigger example in the next video. And you can tell that the freeform controls is because they basically just take in vectors. And this one is interesting. We're going to show this one. We'll explain these all in a moment. Now, the important thing to remember here is all the ones with the purple asterisk cannot start a wire structure. They can only add to an existing one. So if you need to start a wire structure, either start with a Z or start with just a regular this guy append, which gives you a from to. So it'll put down and we'll show that. There's going to be an example how that works. Okay, then there is the, let's go on to now the example that we're going to do. We're going to build a D-wire pickup and we're going to put a magnet in there, but we're going to put the magnet in the Paradox 4 configuration. This is the Paradox 3 configuration. Paradox 4, the magnet will be aligned along this direction here instead of this direction. So let's go to that example now. In this example, we're going to show how to make a wire and a magnet experiment that we're then going to use to show how to demonstrate how to take measurements. So what we do to put in this, we're going to use the same D that we used from the Paradox experiments. Now the difference in the Paradox experiments is that each little section of the coil was separated into a separate wire object in order that we could separate the effects to diagnose the electromagnetic models to see where the electromagnetic models were dumping the energy, what part of the coil. For this example, we're just going to make one coil, which is just going to give us an EMF or a VIM that is imparted by the motion of the magnet M. So let's go do that now. So we're going to go to our application. We're going to bring up our form. Oh, wait a minute. Debug. Let's get rid of all our breakpoints right now, just to make sure. All right, so we want the form. View Solution Explorer. And this comes over here. We want to look at the form. This isn't it. This is the code of the form. We want that too, but not this second. Right now, we want this guy. So we can put in here an example of loop and magnet. Okay, then we click away, and then we double click, and that'll make us a handler for this. So what we want to start off with is some global variables, because you see here in the example, they have loop diameter, which is this, and inner loop diameter, which is that. Let's go make those variables now, and we'll double, and our loop diameter is going to equal meters dot inches. Let's do about a 3-inch loop diameter. Okay, then let's use an inner loop diameter. Now the little inner loop is to allow the experiment to have an axle that could go through without cutting into the crossbar there. And let's make that, I don't know, let's make it 1/2 inch diameter. Okay, and then all we're going to do is we're just going to call it a L for a loop, F2 wire, L equal new F2 wire. Okay, normally we would set all the factory variables here. Okay, but right now all the default variables of F2 wire are what we want. It's copper, there's no current in it, yada, yada, yada. So I'm not going to set. So normally we would set the factory variables here. What we're going to do now is, because the default variables are what we want, we're just going to start laying in the fragments, or the filaments rather. Now what we're going to do is we're going to start from the gap here and work our way around the loop clockwise, or I'm sorry, counterclockwise. So let's start laying in those filaments now. So we're going to start with the hub here, which is TT. And this guy goes from 0 to 90 degrees, 0 to 90 degrees, using the inner loop diameter. Oh, okay, let's set our number of segments in the circle. I think these, okay, let's set that up too. That's something we should always set up now. Let's do that. Int num. Let's do that. Just so we always get in the habit of doing this instead of relying on defaults. And let's just say we're going to say is 72. I always try to do multiples of 36, okay, not less than 36. You can if you want, see what happens, but you're not going to get good results. Okay, segmentation. Okay, I'm setting this to 0 right now because this is a stationary loop and we don't need segmentation on the linear filaments. So let's start rolling this guy in now. Let's go to the now use wire factory controls to build your wire structure. And the first thing we're going to do is put a arc. So we're going to do L append I wish I could type. Append arc Z. Okay, so the diameter is the inner loop diameter. Okay, I'm sorry I can't read this. My color settings aren't the best here, but this is the diameter. This isn't the diameter of the wire. We're looking at this is an arc of a circle, so this would be the diameter or the radius of the arc, actually, but we're specifying it in terms of diameter. We really should use radius, but it's specified in diameter at work, so we're going to leave it at that way. And then the start angle in degrees, which is we're going to go from 0, and the end angle is 90 degrees, and we're going to put in there num segments in circle. Why do we have 2? Oh, that's the little one here with the colon, that is the parameter. So we got that one. So that's our first part. That is what in this diagram is called the TT. So we're going to put TT there just to keep reference of it. Okay, now we want to have this top span here. We're going to use, now we could just put a filament in there, append a straight filament. That would work too. But that means we have to compute the location of this guy here and compute the location here. Instead, the append spoke allows us to append things as if part of this loop. Okay, so this arc spoke things were developed so you can easily put in sections of a very complicated round circular thing using spokes and arcs. And it's all in terms of angles and diameters. So that way it makes it easy to build very complicated armatures. So we're going to do append spoke. And again, the only difference between spoke and append regular filament is spoke is parameterized so you can lay stuff down in a circular armature parameter. And this one we want to go from the inner loop diameter to the outer loop, or just the loop diameter, which would be the outer loop diameter. And you want to have it at the angle, since we are 90 degrees here, that's where our little arc ended. We want to have this spoke at the 90-degree part of the circle. And the other part here is segmentation length, so we're just going to put segmentation length in there, close that. Okay, now this would be this section T. Next, oh, didn't want to double click you. We want to do this loop here. Now, for this one here, this arc, this was specified from 270 to 90. 270 to 90 goes this way. That's going the wrong direction. So we want to go from 90 to 270. So we're going to put in 90 and then 270. So this guy, we're going to append another arc. And it's going to be in the loop diameter. Okay, and it's going to go from 90 to 270. And that is what in this picture is diagrammed as L. Now we're going to put in the bottom spoke. The bottom spoke is going to go from the outer loop to the inner loop at the, and we're going to use minus 90 here. For the important thing to remember is when you're putting in arcs, they go from 2. So if you want to go from 90 degrees to minus 90 degrees in this direction, you have to put 270. Okay, so if this number is bigger than this number, it draws counterclockwise. If I put in 90 and minus 90, it would draw this way. Okay, so you just got to be careful about how you specify your angle. As long as your second angle is bigger than your first angle, it'll draw counterclockwise. If your second angle is less than your first angle, it'll draw clockwise. Okay, so just be cognizant of how those arcs work. As far as the spokes, it doesn't matter. For the spokes, I could put minus 90 or 270 in. It wouldn't matter. It's going to be in the same location. Okay, so the numbers matter for the arcs. They don't really matter for the spokes. So let's append a spoke. And we're going to go from the loop diameter. Well, I guess I can just swap these. And we're going to put that at the minus 90 degree. And this would be our bottom spoke. And to finish it up, we're going to put in our bottom half of the hub, I'm calling that. And again, we just want one of these little arc guys here. Make a copy of him, makes life easy. Okay, and we're going to go from, it's going to be at the inner loop diameter, and we are going to go from, we want to draw in this direction. So we're going to go from minus 90 to 0. Because we want to draw counterclockwise, which means this number has to be smaller than this number. So we're going from minus 90 to 0. We could also put 270 to 360 degrees. That would work too. As long as this number is bigger than this number and it's in the right location on the circle, it'll draw counterclockwise. Okay, so, but we already have minus 90 to 0, so we're going to do it that way. Minus 90 to 0. Okay, and this is BB. Okay, so we have placed our D loop in there pretty easily. You see how quick and easy that was. Let's just take a quick look at it, make sure it is correct. Oh, to do that, we have to L dot, we have to do my universe dot add L, and then we have to put in copy all that, cut out what we don't need. that in there. And now we can take a quick look at it to see what we get. Okay. F2 to put us in a nice location, and loop in magnet. Uh-oh. Did I make a mistake? All right, let's just give this a quick look so we can see if we did it right. We're going to start. Open a viewer. Hit F2 to put it in a location. And then just run the loop. And there we have it. Okay, so next we're going to add the magnet to this. Let's add the magnet. Let's do a disk magnet. Magnet. What did I do wrong? And let's put, now we're going to set, again, we're going to set the, or actually I should call the factory construction variables. Because remember, these are the variables that are going to be added to everything that is done. So now we're going to set the construction variables for the, and what we want is we want M, we want the current to be, 2700 amps, let's say. And I think that's really all we want. Okay, so make sure we add it to the universe before, let's do this now before we forget. And the other thing we want to do is, if we just show what we have now, F5 to run, take the viewer, F2 to put it there, take a look at it. It's in its default position. We should probably make it thinner. Let's make it 1/8 of an inch. The other thing we want to do is we want to move the magnet so that it's end up over the corner out here. So first thing we're going to do is thinnize it, and then we're going to rotate it. Which direction do we want this magnet? All right, we're gonna tilt it up in this along the y-axis. So first we're going to do this, because you have to remember the magnet is built on a frame object, so we can use the frame controls to move this magnet around. First thing we're going to do is just set its, we got to stop, set its width, or is it thickness? Width. No, I don't want wire diameter. Height, that's what it is. Height, meters. That's why it's always good to look at it as you go. Most of the magnets I have in stock are 1/8 inch diameter magnets. Okay, and let's set the, let's make it a 2 inch. Let's put these up here so we can change them if we want. W. Let's make it a 1.5 inch diameter magnet. Okay, and might as well put the thickness there too. That way there we can just change these variables to change the experiment around without having to rewrite code. And let's put that there. It might as well make magnet current too. Equal 2700. Magnet I equal. Okay. Let's put that there. Magnet height. Okay, so next what we want to do is we want to rotate the magnet. Oh, we're going to rotate it toward the minus y. So we're going to take m dot face equal, and that's VXYZ dot rotate z toward minus x. Z faces toward minus x. Okay, and then we want to move the magnet dot PVA dot position dot, we want to move it toward the y-axis, y equals loop diameter over 2. And let's just take a quick look and see what we got here. That would be a function call. See what we got. Check it as we go. View. F2. Example. Okay, so we moved it up. We've got to move it up in Z. And what we're going to do, we want to have an 1/8 inch gap between the wire and the bottom of the magnet. So what we're going to do then is we're going to have a magnet gap. Stop. Magnet gap. So now we're going to add to the Z location of this. We want to move it up in Z by the magnet diameter over 2 plus the magnet gap. And let's see where we are. Okay, and let's just go in. Now, I really should have counted for the thickness of the wire in the gap. It's really, this gap is the distance between the center of the wire where are you? There it is. So let me go up a little bit. So that's what I'm referring to here, this gap. It's actually the distance between the center of the wire and the bottom of the magnet. That's going to be 1/8 of an inch. And that should be roughly the same as the thickness of the magnet, which it is. Okay, so now we have created our little universe of our D pickup ring and our magnet. Now, if I wanted to move the magnet somewhere else, over that D ring, I could just go to the, no, I got to put the magnet in a frame so that I can rotate it around the Z axis. So I'm just going to put another F2 frame and call it W equals new F2 frame. Okay, I'm going to leave it at the origin, and instead of adding the magnet to the universe, I'm going to add the magnet to the frame. So I'm going to add the universe, the frame to the universe, and I'm going to add the magnet to the frame. Okay, see what I did there? Now let's just go look at it real quick. Make sure nothing has changed. It should all be the same. Okay, everything's in the same location. Now, because The magnet is in the frame, and the frame is centered at the origin. I can now rotate the magnet if I want to by taking W and setting its theta, which is its angular offset, equal to 90 degrees. So what I'm going to do, that's going to advance the magnet by 90 degrees. Oh, I'm sorry, that's in radians. Hold on. So what you do here is we say radians dot from degrees 90. Okay. F2 to set a location to view from. Those were, I already had those preset. Okay, see the magnet rotated 90 degrees around the Z-axis. Okay, so we have our little demonstration setup that we're going to use to take measurements with. For now, I'm going to put this Z back to 0, which by taking it out. So now let's get on to discussing how we take measurements of this little experimental setup. Okay, returning from that example, in this one we're going to talk about making measurements. How do you make measurements? How do you compute the effects of one part of the simulation to another? And it's very easy. All you have to do in order to compute the Vim or force on the target loop caused by the magnet is you create a container, F2 Vim for voltage measurements or EMF measurements, F2 force for force measurements. Vim is in legacy volts and force is in legacy newtons. I wrote the software that way because we have to still comply with instruments that measure in legacy components. So I made the output of this. It's easy enough to change in the future, but that's what it is right now. And all you have to do is find the interaction you want. The interaction is essentially what force structure do you want to use? New electromagnetism V5? Do you want to use new electromagnetism V3? Do you want to use classical? All you have to do is get a copy of the interaction and then tell it to compute the Vim, and where L would be the loop and M would be the magnet. This is the target, this is the source. Again, if you want to do force, you say compute force, that should be a lowercase o. Again, target, source. And you would compute the interactions between all the parts you want to compute the interactions on, and then you can add all these things up. It's real easy. There's all the operators are there for doing all of that. Let's go to that example now. In this example, we're going to show how to measure the experiment we set up in the last demonstration section. This is the code we wrote before. And what we're going to do is we're going to make a measurement of the effect of the magnet on the loop of wire. So what we're going to do is we're going to measure the Vim. So we want the F2 Vim. This is a container for receiving results. And we're going to say this is our results. Okay, next we need to get what interactions we want. Okay, and our interactions, I'm just going to call it I. We want to take the default interactions. These are the interactions that are, I forgot where they are. Oh, I'll just get them over here. There we go. We're going to get the default. I'll just copy this. Just do that. Okay, so these are the default interactions that are selected by the menu, and the defaults to new electromagnetism 5.0. And then all we have to do is say results equal I dot, and you say compute Vim. You put your target first. Our target is the loop. I think we called it L for loop. Yep. And our source is the magnet. And then here is where you add the fragmentation length. And I'm sorry for my poor choice of colors here. You can't see this. This little value here is the default value. If you don't enter anything, is 1/10 of a millimeter, which is fine for most of the purposes. And alternately, you can specify your own fragmentation length if you want. This is the length for the finite element analysis. Again, we're going to explain the difference between fragmentation length, segmentation length, and filament length, and how all those interact. a little bit later. Now you have to do this after on local change. You can do the refresh viewers later because this is where all of the spatial effects are computed and taken from local parameters to global parameters. And you need those global parameters in place before you make a measurement. Okay, so as long as this is called and everything is updated, then you can make a result. And then if you want to see the result, right now for this particular setup, we have TB output. That's our text box output is equal to the results are, and right now if you just put the results. Okay, this has a 2-string operator. All you have to do is put it in there. And then I'm intentionally screwing this up to show you something because the results are going to come out 0 because I didn't do something. And you're probably going to run into this a lot because I run into it a lot. So we're not going to bother viewing it. We're just going to look for the results, loop and magnet. And you see the results are 0. The reason why the results are 0 is because I didn't put anything in motion. So what we want to do is we want to have the magnet in spin. So because the magnet is part of this reference frame here, we are going to set the omega, which is the angular velocity of the frame, to radians per sec. How does this one go? Radians per sec dot, and we're just going to do rotations per second and turns per second are the same thing. 4 turns per second, which is what we typically do with the physical experiments. Okay, now that the frame is in rotation, let me put a breakpoint here. Before I do that, let me put a breakpoint and show you something else. And again, you don't always have to view the experiment if you just want the outputs. Okay, so now we're here. Now watch this. If I go up here and I go to the magnet, because I haven't moved anything, if we look and we look at the PVA of the magnet, it says over here its velocity and its acceleration are 0, which means the magnet isn't in motion. Okay, so what we need to do is we need to give the magnet some motion. Because it's in this frame W, we're going to rotate this frame at 4 turns per second, which is what we typically do for our experiments. Now I'm going to set the marker back here, set next statement, and we're going to run it. Now watch this. We're going to, before we show anything on the output, we can look at our results. So our results show that we have -5 microvolts or whatever it is in the coil. So an interesting thing though, and this is very important to understand, we're going to go back to the magnet. Okay, and when the magnet's still going to show no velocity and acceleration, do not be alarmed by this. The body of the magnet doesn't really produce anything for us. So I don't bother computing the PVA global stuff for anything other than filaments, charges, and impulses. That's it. So if you want to find out what the true acceleration of the magnet is, you have to go to the last segment here, or any of the segments in the list. And if we just look at the last segment, and you can see that his global PVA has a velocity and acceleration. Those are properly computed. Again, I only compute the global parameters that are needed for computation for filaments, charges, and impulses. Okay, the body of the magnet is just for display. All we care about is the edge currents, and the edge currents are computed. So there you will find where all of the matrix because if I was going to do it for every object, then every time I update it, I got to update every stinking object, even though they produce no effects that we're measuring. Okay, so understand that it's only filaments, charges, and impulses. There might be something else, but it's basically those three. Okay, and of course, we're going to let this continue so we can see the output here, and the results are, what is it? That's 57 nanovolts. Nanovolts, yeah. Okay, now we're going to, let me see where the magnet ended up on this. Oh, okay. If we want to get more voltage right on the line, it's null. Let me move it off just a little smidgen. Okay, so we'll run through this again. And then what we'll do is we'll move it off a little bit. We'll add a little theta. And we'll add, 2 degrees of theta. We just have to be off the wire a little bit so we don't get a near zero answer. Let's go back up there. Set next statement. Now, you have to call, because this is a construction parameter, it's actually a local parameter. We shouldn't need the on construction, you just need the on local, but it doesn't hurt to call them both. Okay. And now our results are much, much, much bigger. We have 334 microvolts. So we've gone from 57, I know that's kind of small. Let me run it to the end so you can see it in the box. No, that's still small. Okay, so that's sometimes you have to add a little offset because being right on the line, that's where everything is null. So that's why, oh, and you can see now it'll be a little bit off. The magnet's not quite exactly on the wire. It's rotated off a little bit. Looks like it's bent, but that's an optical illusion. Okay, next. What I want to show you is you don't have to use the default interactions here. Let me get the breakpoint around again. Okay, the default interaction just allows you to select one of the interactions from the main sheet, the ones that are selected from the main sheet. I'll show you that in a second. You don't have to do that. You can just say new FZX2 and you've got all these. You've got classical 1R, classical S. If you want to use new electromagnetism V3, you put that in there. And so you can select any of the ones that are available programmatically. If you want to use the default is selected. Of course, I have to go up here and start again from there. And you can see the results are different because new electromagnetism V3 does not have Coriolis effects. So that was the reason why we went to new electromagnetism V5. It's there if you want to use them. Now, when you first start up this program, let me start it up again so you can see what I'm talking about. In the beginning, it'll tell you all of the things that are in there, but none of them are complete. What you have to do is come down to these readouts down here, and it'll tell you with these little brackets and the stars which ones we do not have forces for. Okay, so new electromagnet, a lot of these were just put in there so we can do simple tests with the paradox 1, paradox 2 for comparison. Okay, any V5 is missing some small effects. I think it's missing one effect. And new 5.2, we don't have the new we don't have the anti-gravitic effect for, so you just got to go through here and find out what's missing. Now you see these F1, F2, F3, F4, F5, and then you see V1, V2, V3, V4, V5. What these will do is they will put the different effects into different containers in the result. So you can see what the different things, so in other words, F1 has the Coulomb and the anti-gravitic. F2 has impulse, source from wires, venturi, and centripetal combined. F3, I know that's tiny. I'll blow this up so you can see it. But essentially what it means is you can take the different effects here, and let's do that now. Oh, the defaults are set here. So if I change this, it's defaulted to this even though you don't see a checkbox. But then when I hit that, it's checkbox now. That will be in the default. So if I pull the default, it'll use the 5.02. If I click there, so these set the default right here. On power up, it defaults to 5.0. If ever you don't know, you can just hover over what you got, and it should oh, we're out of scope. Okay. So let's go back to setting this to the default. Okay, so let me show you what I mean by the different 5 containers in there. Okay, so if we go into the results, you have Vim 1, 2, 3, 4, and 5. And so these are the separated, and these, all you have to do is look up, you can save what it said on the front page, and it'll tell you, what the purpose of the V3, the V4 is. And so you can separate your results. When we get to the measurement plane, you can do some more interesting things with these. You can tell the measurement plane only to display the V3 or only display the V4. In fact, it gives you an array, and so you can even negate the V3 or the V4, or multiply it by 2, multiply it by whatever you want for your measurement plane if you want to play around with the effects. Okay, for this also, if you just don't want to use a regular 2 thing, you can break them out. So instead of doing this, let's go back. I'll do that in a second. So is equal to. Oh, I think we have a get string. If you use the get string, let me set to. Can we go back, and then we'll run this out. Okay, so if you do the get string, it'll dump these out separately for you with the total at the bottom. Okay, so if you use the regular built-in toString, you just get the end result. If you use the get string, it'll give you this display here. So it'll break them out for you again. And if you want to see where these, what's in each one of these boxes, that's in the, when you power this up, it'll show you, which box, what forces go into which boxes. Okay, I think that's a good enough demonstration. Okay, now to put a little finer point on what you just saw, their measurements are all derived from an interface here. And all you have to do to create your own interactions is just override all the functions, or provide the functionality for all of these functions, and you can produce your own interactions in case you want to experiment. And if someone wants to do that, let me know, and I'll make a video that shows how to do that from scratch. I don't expect people to be doing it, but I'm putting it out there in case somebody's interested. Also, all the available interactions are visible at power up. When you first start this application, it's going to dump all of the available interactions. The default interactions are set by this menu item up here. Right now, you can only set the default to either 5.0 or 5.2. If you want to use the other interactions, you have to use the procedure shown in the demonstration. Now, the important version number here is this FZX. Okay, this is 2.02. That is the version of the physics library that we're using. Don't worry about this. This is just the version of the shell. That's good. That's not important to us. This is the important one. That's the version of the effects and the version of the components you're getting. That's the library. And this is the component, the version of the drawing tools that we're using. Those have been updated as well. Now, another important thing, we're going to talk about that later. The other important thing is when you scroll down a little bit more on the main menu, each one of these force interactions shows what parts of them are missing. Like for V3, I don't have the full gamut in there. I have just enough to do the interactions for the paradox experiments, and the same with the classical and the classical T. 5.0 is not complete either. We still are missing a filament to F2 charge. In other words, the effect of a charge on a filament. I'm not going to complete these now because I don't have a means to validate those experimentally. And so what will happen if you accidentally run into one of those, it'll throw an exception. And let me show you what that exception will look like. Okay, this is the class for the 5.0 interactions. You see it's derived from the interface interactions. This is the text that you see that's dumped out at power up. It shows you what's missing. If ever you hit something that is missing or not handled yet, you'll either get an exception for unhandled object type. Okay, meaning if something else goes in here that shouldn't be going in here, it'll throw an unhandled type. And down here where it computes, like for example, we don't support charge imbalanced filaments. So if the source charges and the target charge is not equal to 0 either or, it's going to throw a not supported yet exception. And down here where we're computing the charge on a filament, you're going to get a not implemented exception. So if you get those, it means that those are the incomplete parts. I'm not going to give you nonsense answers. I'm going to give you you're not going to complete your experiment because I don't want just to give a 0, which might give somebody the wrong answer. I want to actually have you end the experiment if you hit these. So far, I haven't hit any of these. If when I do hit them in experiment, that's when I fill them in. Okay, so that's that way there, because otherwise there's so many more that need to be added. I'm going to hit them as I go. I know this is left undone, but at least it's going to throw and not let me make a false judgment about something. It's going to actually stop and say, sorry, buddy, can't go further here. Next. Okay, so this is the line of code when this sets the default. This is how you pick up the default that was mentioned in the example. Okay, now we're going to cover the importance of segmentation. What I have here is an example. I have a spinning wheel, and on the spinning wheel we have one uniform filament, and we have another uniform filament over here. Now what happens on local change, this computes all of the global parameters for the important objects, meaning the filaments, the charges, the impulses, etc. But what it does is it computes all of that at the center of the wire, or the center of the filament, and for the center of the filament. Now, when you take your measurement, okay, this one here, this is your fragmentation length. This is your differential length. This is where the finite element length is specified. Right now it's all defaulted to 1/10 of a millimeter. So what happens in this compute the VIM filament to filament is the filaments are chopped up into the lengths, an even number. I mean, there's no fragmentary. They're chopped up into these tiny little lengths, and then for each one of these is computed against each one of these. It's a double line integral essentially. And that's how the effects work. And that's how they're computed. Now, normally, for the velocity, acceleration, Coriolis, all this stuff that's computed at the center, I'm just using VACC here, this is not a problem if these filaments are translating uniformly. In other words, they're not rotating in any way. This will work perfectly. Okay, this was actually copied over from Physics 1. That works pretty good. So you could only have to specify the whole length of the filament. You don't have to automatically segment them. Now the problem that comes in is this: if this is in fact rotating, well, on this wheel here, the centripetal and the Coriolis forces at the top of the wire are going to be different than at the bottom of the wire. Now normally if your target is very, very far away, that might not matter. But since this guy is right here and these components are closer to the top than the bottom, then the average of all of these things at the center is not going to work right. So what we need to do, because right now the software does not go out because. So what we need to do is segment this into smaller filaments so that the VACC is computed for each one of these alternating filaments here. So that when it is finally chopped up, each one of these filaments are chopped up separately and integraled against this. And it doesn't seem to take that much more time to do this. Now in the future, I want to retroactively fit the software from the graduate thesis, which figures out all of this stuff automatically so you don't have to specify it. In other words, it does automatic segmentation and differential length computations to figure out what you need for every interaction between all the pieces. So you don't have to specify this, because if you specify these things wrong, your segmentation and your fragmentation, your experiment can either take way too long or it won't be accurate. And let me show you an example. Now, right now, the typical values for fragmentation is 1/10 of a millimeter, and the typical length for segmentation is 1 millimeter. If your experiment is much bigger than the small paradox experiments we're working on, you'll have to make these larger. If your experiment's much smaller, you'll have to make these smaller. These have to scale with your experiment. So basically, the way you do it is you pick a set, okay, look at a value, and then you increase them, like you double them each time and see if the value changes. So you can see here that the standard segmentation length we use is actually pretty good. This gives 305.421 microvolts for that experiment we just saw. Okay, when I make everything bigger, it doesn't really change significantly enough, but you can see that the processing time goes up. So that's what you have to do is when you're making your own experiment, you got to find the sweet spot for these values for segmentation and fragmentation. Okay, next we're going to discuss the free-form wire controls. We're going to go off to that video now. In this demonstration, we're going to show you how to use the free-form wire controls. Let's go back to our form, under example, and free-form wire. All right, let's just make sure we put the clear all. If you don't put the clear all, nothing you do is going to come out because it won't be set up properly. Make sure you do the clear all first. And then we'll put these 3 guys at the bottom. Excuse me. So what we're going to do is we're going to do everything in centimeters now. Okay, we're going to define a straight segment length. We're going to use a default centimeter. Okay, just so you know, in this little meters thing, you can specify AWG, which will give you the diameters of, let's say, a 30 gauge wire. And that's how, when I specify default of something is 30 gauge, it's in meters, but it comes from this thing here. Okay, but we just want centimeters, a little segment there, and then we're going to have a diameter. Excuse me. Let's make a diameter of 3 centimeters. Okay, next, we're going to put our F2 wire object in. I call it W for wire equal new F2 wire. Set all the factory controls. Okay, right now I'm going to start off with a segmentation of 0. Segmentation length. Okay. So let's go look at our controls that we have, and this is our updated. Okay, that's the Z-plane, and we want to go to these are the free-form controls. Now, all of these ones with the purple here, you can't just put in. You have to have these only append to the existing wire structure. So we're going to use the very first one to put the starting fragment in, and we're going to go from the origin to 1 inch in X, or 1 centimeter in X. So we're going to do W dot, let's make our starting vector first. M vector 3 equal new 0, 0, 0. And we're going to go to, let's go to, all right, let's just start this in the positive y direction. Straight. Two. So W dot append. Okay, and we want the append that takes vectors, doesn't have a z in it, and we want to append, we don't want the filament one, so we're just going to put the start, the 2, and we're going to set the segmentation length, because we may want to change that later. Okay, let's make it all lowercase. All right, let's just take a look-see at this to see what our, let's open up a viewer, set it at, I guess that's a good enough location as any. And then we're going to run this freeform wire. Let's let it run. And it made a liar out of me. Okay, I forgot to add it to the universe. It's a common mistake I make. Down here, let's say my universe dot add wire, and let's go back up here, set next statement, and run. Okay. Oh, I gotta let the reviewers refresh. Okay, so there's that starting filament right there. Let me zoom in on that so we can see where we are. I'm going to save this as Shift F3 so we can come back to it if we need to. Okay, so let's go back in here. I'll put a breakpoint here so we can continuously run this. And we're going to do freeform wire. Next one I'm going to do is I'm going to append an arc. Let's show you the arc command. So the first one we did was the from to segmentation length. You can put a filament in, it goes any direction. It doesn't have to be in the Z plane like the Z controls do. Okay, and so what we're going to do now is we're going to append an arc. And so the diameter of the arc, we have the angle of how much of the angle we want to go in degrees. We have to define what up is so it knows which way to roll. And then we're going to let it default to the number of segments in circle 72. So what we're going to do now is we're going to do W dot append. Okay, not Z arc, regular arc. Okay, and so the diameter, I'm going to use the diameter, this guy. Let me get this guy out of the way. Okay, and then we need the angle degrees. Let's do, let's do 180 degrees. We're going to go halfway around the circle. And then the vector, next one, sorry, I got bad colors here. They don't show up. Diameter, angle in degrees, the vector, the up vector. So right now I'm going to use a normal up vector of Z to show you it work. If you put this to Z, let's make an up vector. And let's make our up vector in the Z direction. Okay, and then let's go down to, I can put a breakpoint there. And, We need to put the up vector, and we can leave the number of segments blank. Okay, and I'm going to run to the other breakpoint. Okay. Okay, now we're going to let this go and see what we got. And there's our arc. What I'm going to show you now is I'm going to change this arc from it being in the Z-plane. I'm going to change it to going up in the air toward the Z direction instead of being in the Z-plane. So I'm going to define up as going in the positive X direction here. Let me just run back to here, set next statement, and then we're going to run down to that breakpoint and then that breakpoint. And now you can see it's going up in the air. All right, I got to let it run so I can get control of the form back here. Okay, so now you see it's going up in the air. That's cool. Now let me show you another one of the wire controls. We have this normal just append length. So if I just want to continue the filament in a particular direction, all I have to do is append an integer length, and that'll just append a new little length to it. Now let's get back into, let me get this off. So now we're going to say w dot append, and then we're just going to put straight. We're going to use our straight variable, straight, comma, segmentation length. We're going to run that guy down. So I can just keep adding straights. And then let's go around the curve. Let's put a new arc on this. Let's make this in the, let's make it in the minus y so it goes around. So we're just going to put new and vector 3, 0, comma, 0, comma, minus x. Oh. Okay, so now it came up. Curled around the right. Now we want to make it go back down. We want to put another straight section on there. Let's add another straight section. And let's add another arc. And for this one, we want to curl down this direction, which means we want the up to be in the minus y direction. And then might as well finish this. It's going to be down here, and I'm just going to add another straight section to the end. Okay, let's run this guy. Oops, I made a mistake. What did I do wrong here? Oh, that's weird. Oh. Yep, okay, this is a mistake. I want, okay, you can see I forgot to remove that. And so it's really, this is interesting. We've got it's kind of at a weird angle. So you can define your up in any direction you want here. So this is kind of like an angled up. Not what I wanted, but you get the idea. So what we're going to do is fix, actually what I wanted it to be is in the minus x direction. So let's get back in. I want this to be in the minus x direction. Set all these other guys to 0. See, that's why it's good to have a view of what you're building so you can make sure you're building what you plan to build. So that's what I plan to build to show you how to use the freeform. We'll have another example of the freeform wire controls where I show you how to build a coil. Okay, but this gives you the basic idea that with the freeform you can just keep, and then if you want to, also if you want to just go off at a 45-degree angle, we can do that. But that requires us to use the other last control here, which is append vector 2. Let's do that one just to get so I can show all of the different controls. And let's get the breakpoint to here. Let's get back in. And then we're going to add a 2. We're going to go to, I don't know, let's go out to, let's just make the end go out to -3 in y. W.append new 0, -3 in y, -3 centimeters, and then segmentation length. Now let's see if that works. There we go. So with these simple 3 little controls, you'll go with the 2, the straight, there's 4 controls actually. You can build any wire structure you like. So this ends the demonstration of the wire, the freeform wire controls for the wire object. Okay, returning from that video. Next, we're going to do the indicator plane example, going off to that example now. In this example, we're going to add a measurement plane to our loop and magnet experiment. So let's go to the data sheet for the measurement plane. Okay, so we have a width x, which is in the x coordinates, y, and then number x, number y. That's pretty much all we need. So there is an indicator plane 1. You can use it. It's not recommended. It's kludgy. This is the improved one. Indicator plane 2. F2 indicator plane 2. So let's go to our loop and magnet experiment and let's put a breakpoint in here. Where is it? It's over here. And let's get into it. Okay. So we're going to have indicator plane. Yeah, just put it here. F2 indicator plane 2. Okay, now all we have to do here is set the construction parameters. Dot width x is equal to, okay, so we have the diameter of the magnet here. So let's make it twice the loop diameter in x. And let's make the same for the y. And let's just say the number of sample points in x. Let's make that, I don't know. Let's make it, let's just start with 32. And we'll do the same for y. Now, it's built in a frame, so you can move this, use the frame controls. You can move this indicator plane anywhere you want. But again, everything defaults on the Z plane. Okay, so it's right where we built our experiment, so let's just leave it there. Okay, but essentially you have the full frame controls to move it wherever you like. So I do need to go back and rerun this part so that we can add that. And then we want to take a measurement. All you have to do to compute the, well, I'm going to omit this step so I can show you what happens if you forget this step, so you know what it looks like when you forget it. So I'm going to let it run. And you see absolutely nothing. Oh, I forgot to add it to the universe. That's why. They keep doing that. My universe, add my plane. See, I'm showing you the mistakes I commonly make. All right, I'm just going to let it run. Now, when you put an indicator plane in, it takes a little bit longer to run because it's got to compute 32 times 32, 1,000 charges. So just open you up, set you to 2, and then just run you outright. Okay, so there's a reason why there's no visible plane there is because we haven't computed anything for it. Now watch what happens. Oh, I got to stop this again. All you have to do, you don't even need the results. You compute. The target is my plane and the effect from the magnet. Or would that be force? Oh, I think we got to compute 4. Oh, let's see what happens. It'll probably, I think I'm supposed to do view, F2. Okay, I think I got to do compute force. Yeah. There you go. Okay, so you will not see the indicator plane if it has not been computed. Just remember that. And now you can see all of the effects of the magnet. Now, here's an interesting point. In the controls for okay, you want the coefficients. The default is 1. If you remember here, you look at this guy, that we get a certain effect here. I believe that's the magnetic, and this is the Coriolis effect. So if we, right now, since this coefficients thing in the indicator plane defaults to 1, 1, 1, 1, all of these guys are multiplied by 1 and applied to these little charges here. If you just want to look at 1, the effect of 1, let's look at just the Coriolis. So let's do this. Let's run through. See, make sure there's a breakpoint there. Do it at the indicator plane. Get back into the example. And I'm going to say my plane dot coefficients equal new. Oh, it's already there. I can just say coefficients. No, let's just do it this way. Equal new. Float. 0, 0, 0, 0, 0, just to make sure I have everything. I got the wrong symbol here. Okay, I'm fixing it. So we want to look at what's in slot 3. So I'm going to put a 1 there and let this guy run. And you'll see this guy over here change. Okay, see, that's definitely the Coriolis force. I ran it this time with the coefficient set to negative, and the arrows are definitely going in the opposite direction. Let me just do this one last try. Let me just clear all the breakpoints. Okay, all the breakpoints are gone. And let me stop it. And let me set it back to 1 and set this other guy to 2. See what that does. Okay, that worked. Okay, so let's set this back to normal. And let me show you one last item of importance with, let's put this back to, let it go back to default. Okay, one last thing that's important with the measurement plane is that you can dump all of the information. These residues you can figure out in yourself, but you can dump all the information into the get. Okay, I have to update this page, but what you can do is at the bottom here, you can say, take your my plane and say TB, and you put this to a file too. Plus equal, and let's put some carriage return line feeds plus my plane dot get report. Okay. Wait for it. Okay, so there's the report. This is dumping all the sample points in the report plane. Okay, so the first vector, the first 3 elements up to the semicolon. Let me see if I can't blow this up into Notepad for you. Notepad. Okay, so the first vector, which the vectors are separated by semicolons. The first vector is the position of the sample point. The second vector is the velocity of the sample point, and that goes up until the next semicolon. And then you have a dumping of each of the individual forces, F1, F2, F3, F4. You get the idea. And then the final vector up there is the total, the summation of F1 through 5. And that's all this is all the way down. You can dump this report out to a file. You can do whatever you want with it. Bring it into a spreadsheet, yada, yada, yada. Okay, that's the last I'm going to show about the sample report. There's other controls there for if you have multiple ones on there and you want to normalize the colors between them. That's what these are for. If you want to get the max amplitude in the set, but you can do that by dumping the report and looking for it with whatever tool you want to analyze it with. Okay, that ends the demonstration of the sample plane or indicator plane. I call it the sample plane, indicator plane, whatever. Okay, we're done with this video. Let's give a review of what we talked about. We talked about the wire factory controls, And we have two major forms. We have the Z-plane and the free form. We showed how to take measurements. We talked about the importance of segmentation. Again, in the future, we'll make that automatic, so the software will figure it out on its own. That is doable, but it's a big software update. We want to make sure we get all the software working right for the physics first, and then we can make updates to make it more user-friendly. And then we talked about how to use the sensor plane, and we showed how to dump the data collected by the sensor plane. The one thing I left off is if the sensor plane is a frame. So you can spin the sensor frame, and each one of these little spots here is basically a charge of 1 coulomb. So if you spin it, these are going to have centripetal velocities, Coriolis velocities, yada, 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 and that may couple differently to your magnet, whatever your force is. So you can actually move and translate these frames to explore other effects. The next video, we're going to go into F2 containers, and the main reason for those is to offload all this code we're dumping into the main form and make it reusable. We're going to show you how to make a coil, and then we show you how to take a sequence of measurements. We're going to continue our loop and magnet example by sequencing it. And we're going to show you how to make experiments responsive to the controls on the front panel and show some simple animation controls that are built in. And then we're going to show how to make other types of measurements like inductance and resistance. And that, I believe, will be the last video. Later, I'm building up the Stern-Gerlach experiment video series, and we're going to demonstrate how the experiment is done with FZX2. And later there will be a PDF that explains all of the built-in experiments on the main bar up here. These are all the experiments done to validate new electromagnetism V5 and some visual aids. Okay, thank you to all my Patreon folks. You guys are the best. Again, if people want access to this software right now, it's available to engineers and above Patreon members. It will be when it's published. It'll be published after the last video is done. This is the main repository. I've been having big problems trying to get the new site up there. I'm trying to figure that out, but I'm really not putting that much time to it. I'm trying to get the videos done. This is the blog site. Great shout out to Sebastian for taking care of this. Again, when I'm able to make more time, I'll spend more time here. I apologize. This is the main place where the YouTube videos are premiered. They're typically premiered on Thursday nights. I will show up here in the community section. I will post an upcoming schedule of releases. And thank you. That's the end of the video. I forgot to put the end screen that no more voodoo physics. Have a good one.